Hello, and welcome to another wonderful episode of the New York City Category Theory Seminar. Today we have Morgan Rogers, and he's going to talk about ultra categories. I thought it was ultra rings. Okay, we changed. A categorical approach to unifying
It's
Boolean.
just a typo in the title. I am talking about ultra rings, and that is kind of tragic. But there we go. These things
Anyway,
happen.
a categorical approach to unifying Boolean and algebraic descriptive complexity theory. Take it away, Morgan. So remember the four things.
Hopefully
Go.
the title on the YouTube video can be correct at least.
I will change
So
it. Don't
I'm
worry.
Morgan. I'm originally from Shrewsbury in England. I did my bachelor's and master's at the University of Cambridge, also in England. I did my PhD at the University of Insubria in the north of Italy, and I'm now based at the Laboratoire d'Informatique de Paris Nord, LIPN, which is, as the name suggests, if you know a bit of French, just to the north of Paris, although not technically inside Paris. So maybe it's slightly misleading. So here we go. I'm going to be talking about ultra rings. Ultra categories are a very interesting subject, but that's not at all what I'm talking about today. So please forgive the quite embarrassing error. So the structure of the talk is going to be as follows. I'm going to motivate the things we're going to do, starting from an analogy between how we present rings in particular, but algebraic structures more generally on the one hand, and how we present theories in first order logic. So we have syntax for algebra and for logic, you might say more generally. But if we kind of focus on two things that we want to link together, then we can end up with something in between, which is quite interesting. So in the second section, I'm going to motivate those two classes of what we would like to be examples of ultra rings. Then I'm going to give a definition based on the observations that I'll make about those examples. And then I'll return back to the analogy from the start of the talk to show how we can still have a kind of syntactic presentation of these things. And then I'm going to make the connection promised in the title with complexity theory and explain what the initial goal of this work is and where we're hoping to go with it. Okay. So first of all, let's do some fairly basic stuff and talk about presentations specifically of rings. So if I want to describe a ring to you, one way that I can do it is I can give you some generators for the ring, and I can give you some equations between polynomials in those generators. And then I can take the quotient of the set of all polynomials in those generators by those equations, and that will give me a ring. Okay.
Morgan, you're
One thing you might be surprised by in that.
Morgan, back up 3 sentences. You were slightly, your network bandwidth is low. So
Imagine.
just, okay, fine.
I'll back up 3 sentences. I'm going to start from the end of this sentence. We have a way of presenting rings in terms of generators and equations, and you might be more used to generators plus ideals. But this is equivalent, and this also works for semi-rings. So it allows more generality, and eventually it's going to look a bit more like the end product that we're going to end up with later, but we don't explicitly use that generality in the talk. But anyway, whether a set of equations or an ideal, we have presentations for any ring. You can still hear me, right?
Yes, yeah.
Okay, good. Okay. So what does a presentation do us? It gives us a mapping out property of our ring. So if we write S in this way as a collection of equations between polynomials, and I want to consider a solution to those polynomials in a ring, that is a selection of a value for each generator, which have to satisfy those equations, then I can view that as a ring homomorphism from this quotient ring to R. But more specifically, it's a factorization, or it's the fact that this choice of collection of elements satisfies those equations amounts to saying that I can factorize the corresponding homomorphism from the free polynomial ring through this quotient. So this is also a diagram that we're going to come back to right at the end. But the commonality with what we're about to see is that where here we can view ring homomorphisms as a collection of elements of a particular kind. In the next section, we're going to see it as a model of some kind of theory. Okay. Now, I'm not going to assume that everyone is super familiar with categorical logic or logic more generally. So if it makes you more comfortable, just think of what I'm going to present as syntax, which superficially, like just looking at it, looks like what we just saw, maybe with a few extra ingredients. So if I want to formally present some kind of mathematical object, the really traditional way of doing that is to use first order logic. I have some collection of sorts, which will get interpreted as collections of elements of one type or another. Then I have some symbols, some formal symbols expressing relations between those elements or subsets of those elements. And then I have formulas which control the relations between the relations, if you like. So I can express the axioms of, say, groups, any algebraic thing that you might be familiar with, in terms of first order logic. And now we finally get to the category theory. If I fix the fragment of logic, which is to say I fix the tools I'm allowed to use to build formulas, then each way of constructing formulas corresponds to some categorical structure, and there is a natural way to go from a theory to a category with the right structure to interpret that theory. I'm not going to go into a lot of detail about the general process. It's okay, I do mention Lorvier in a little while. But the point is, I can go from this syntax to some kind of category. That's the main thing that you'll need to retain. And specifically, the kind of category that we're going to be looking at is what's called a Boolean lextensive category. So let me unpack that on the next slide. So lextensive unpacks into lex plus extensive, where lex itself unpacks into left exact, which is an old-fashioned way of saying having finite limits. Extensive means that those limits interact well with finite coproducts. So in the same way as in the category of sets in particular, if I can express something as a disjoint union of two other things, and I have a map into that disjoint union, then I can decompose the domain of that map as a coproduct, where each part of the coproduct lives over the parts of the codomain. And finally, the Boolean part is saying that each subobject in my category, so as a reminder, a subobject is an isomorphism class of monomorphisms. So in the category of sets, a subobject is a subset. And we're asking that every subobject is complemented. So there is some other subobject such that their intersection, which is constructed as a pullback, is the initial object, and such that their union is the full object. So there are a few ways of expressing that last condition. I won't belabor the point. I think intuition from the category of sets is plenty to be going on with. So the consequence of these definitions is that the structure that we use to interpret logic into like formulas in terms of subobjects is preserved under pullback thanks to this extensivity.
Are you using a full first order logic or a fragment?
This ends up being the fragment where we only allow provably unique existentials.
Got it. Thank you.
So this is the difference between taking the Boolean lextensive categories that we have here and taking Boolean coherent categories. So in a coherent category, a coherent category is in particular regular. So we'd have images. Each arrow in the category would determine a subobject of its codomain via a factorization system. And we don't assume that factorization system here. And if you think about that when we get to the examples, you might see why that's the case, because the existence of that factorization system would force us to have more objects than we want to keep track of in the kinds of category that we're going to end up talking about. I hope that wasn't too cryptic, but ask me again at the end if maybe I can clarify it better.
That was good. Thank you.
Suddenly started raining very heavily. So, some observations about these categories. First of all, I can extract a theory of the kind mentioned previously from a Boolean extensive category such that this category is exactly the syntactic category of that theory. So I can really go between theories and categories, and maybe there's some identification in one direction. So different theories can present the same Boolean extensive category, but this at least we can we know that first order theories are enough to reconstruct them. Now, as I mentioned previously, the reason that we care about choosing a class of categories is because these are the categories in which we can interpret all of the logical connectives. And so when I have any first order theory, I can make sense of models of that theory inside a Boolean extensive category, because the latter will have enough structure. And in classical functorial semantics fashion, those correspond to functors which preserve the demanded structure out of the syntactic category of that theory. Okay. That looks strange. Okay, to ground things a little bit, we have the category of finite sets. This is going to be something that we'll return to a bunch. It is a Boolean extensive category. That's why I was referring to a category of sets earlier on to motivate the properties. And models of a first order theory inside finite sets are just finite models in the usual sense of that theory. Okay. So a theory that's going to be important to us later, but that I won't make explicit until later because I'll need to present it in slightly different terms, is a theory of strings, which is to say finite total orders where I associate to each entry a 0 or a 1. So I call these strings because I could just ignore or incorporate the total order into the structure and interpret a model of this theory as 0, 1, 1, 0, 0. The point being that the order is incorporated there. So the reason we care about these from the complexity that's coming much later is because typically we can encode the solution to any kind of computational problem in terms of a binary string. So if we're working with Turing machines, for example, the tape of the Turing machine is going to contain one of these strings, and depending on how you encode things, if you're a purist about encoding everything into a Turing machine in order to talk about it computationally, then that's this kind of structure is what you end up looking at. So, by analogy with what we saw previously, if I take an extension of this theory of strings, so that is, I add axioms which ensure that I don't have arbitrary strings, but strings which satisfy some extra property, say, are a witness of a solution to some problem, then I again get this factorization property. So an arrow S like this corresponds to a binary string, and it will factor through an extension of that theory of strings if the string satisfies the extra axioms that I've added to obtain T. So this is how we're going to encode computational problems, and what the relation is between those problems and the Boolean lextensive categories that that are going to be recurring throughout. And by the end, we'll see, or I'll at least tell you, in what sense we can capture complexity classes in terms of these extensions.
So your bit strings are playing the role of polynomials as the free object, free things here.
Yes, they're replacing the free things. So we're thinking of T as what we get by adding equations and possibly more, but as more constraints on strings.
Is the vertical map a quotient map?
Not necessarily. So if I am just adding axioms, so I'm not adding any extra structure, then it will be a quotient map. But this is flexible enough to allow for extensions where I add sorts or relations, and that will still it would still be the case, but this dotted arrow would no longer be unique necessarily.
And the theory of strings has what, one sort and two unary relations for 0 and 1?
One sort, a binary relation for the ordering, and a unary relation to identify which bits are set to 1.
Okay.
So here's the big idea. By presenting these things side by side, I'm implying that there's some analogy between these things. Now, what I didn't say on the ring side is that, of course, we can take a ring and we can produce a category from it, and we can think of that category as also being produced from the presentation. So what we want to do, no, I think I meant to have a footnote here, is derive categories from Boolean extensive categories or rings. And I say derive from Boolean extensive categories because, in fact, the thing whose properties I've described is not exactly the categories that we're going to be abstracting from. So we're actually deriving categories from both of these cases. And we're going to come up with some definition that includes both of the results. So we want those to be structured enough to allow us to do algebraic geometry. That's a spoiler for the very end of the talk, I suppose. But we want to be able to transport tools from all the things we know how to do in commutative algebra to the complexity theoretic problems that we want to talk about. And what I'm going to spend a lot of the talk on is talking about presentations of the resulting structure. So we really want to think of the presentations from the beginning as also being two instances of presentations that we will be able to apply to Ultrarings. Okay, so let's deepen those examples. The starting point you've already seen, but let's swap the order this time. So
Morgan, you're slow again.
in a Boolean extensive category, between these categories and theories. Okay, on the relationship between Boolean lextensive categories and theories that I just described, I can think of subobjects in a Boolean lextensive category as formally representing propositions. So maybe depending on how I've presented one of these things, not everyone is literally a clean formula, but because I can present everything in a syntactic category from the signature of the first order theory that's used to build it, this is more or less literally true. So the reason that we stick to Boolean things is partly because all of complexity theory happens in a classical logic setting. So I spend most of my time doing topos theory, so sticking to classical things is not a particular concern of mine. But one convenient side effect it has is that the coproduct of the terminal object with itself is a subobject classifier in a Boolean extensive category, which is to say that arrows into 1 plus 1 correspond to subobjects. And so that's something that we'll always have access to because by assumption, these categories have coproducts and terminal objects. And rather than staying within this category itself, so here we already have a presentation of subobjects as arrows, but what we're actually going to do is move to the partial map category, which is to say the Kleisli category for the maybe monad, if you like. Then arrows from A to 1 plus 1 in the thing that we started with will now be arrows from A to 1 in the Kleisli category. Now, we'll see from the similarities of the next example that this shift is kind of justified. But one motivating reason early on was that it meant that the things that we started from, so in one case, the truth values, the subterminal objects for Boolean extensor categories, and the ring that I was presenting at the beginning will be recoverable from the categories that we'll end up with by looking at endomorphisms of the terminal object. And it's easier to talk about endomorphisms of a single object than arrows from one object to a possibly ambiguous second object. Okay.
Well,
so this is the category that we
before you go on, just one quick question. Not a question, you'll probably talk about it later. I mean, complexity theory is not totally Boolean. In other words, not there exists and for all are two totally different operations that take, you lose the symmetry there. I don't know if you're ever going to talk about for all, universal quantification, but maybe you'll just stick to existential, but there is an asymmetry there. Okay,
anyways, that's true. I think it would have been possible to not just talk about NP, but talk about co-NP towards the end of the talk. But it's not something I'm going to explicitly mention. So I'm glad you've asked. The sense in which we are working classically is the fact that we can, firstly, we have access to negation as a basic logical connective with the expected properties. And when it's not interacting with quantifiers, then things are sufficiently symmetric.
Propositional complexity theory is totally symmetric, but when you get to predicates, it's painful. Okay, go on. Never mind.
My co-author would have more to say about it, but I hopped on the bandwagon for the category theory, so I might not be able to give a particularly satisfying answer to what extent the structures we end up with are, in an essential way, Boolean. So let's have a closer look at this Kleisli category. And the next few slides are going to be quite dense with categorical properties. I have time, so I'm going to use it. So firstly, this inherits coproducts. So they're the same as in the original category. But moreover, the initial object becomes a zero object. So remember, that means it's both initial and terminal. And that actually means that we can more easily construct certain maps into coproducts. So, for example, there are some maps into coproducts that we can construct as soon as two objects are, as soon as two partial maps are defined on disjoint subobjects. On the other hand, becomes a monoidal product. So we have a monoidal operation that acts in the same way as the product in B on objects, but it's slightly more subtle on the maps. But the important thing is it's not the categorical product anymore. I'll mention the categorical product in a couple of slides' time. The relationship between these is also inherited from that between products and coproducts, namely the former distributes over the latter. And we also get some structure that is normally associated with categorical products, namely the diagonal and the terminal maps become maps associated to this tensor product, but no longer have the same universal property. So we can also turn monomorphisms around. So if I have a monomorphism one way, I can think of it as defining a partial map in the opposite direction. And that means that we also get the duals for both this diagonal and the coproduct injections. Okay. Final observations that are particular to this setup. One is that if I take partial map from A to 1, so remember, that's just an arrow in the Kleisli category, but we know that that just corresponds to a choice of subobject of A. If I look at what happens when how this interacts with the tensor product, then it's idempotent in this sense. So it's not meaningful to compose it with itself to be idempotent in the usual sense, but with respect to this monoidal operation, it's idempotent, where this delta is the diagonal on A. And we can also characterize the complement just in terms of how it interacts with the structure in this category. So I get the zero map on one hand when I take the equivalent of the injunction, and this is how we can present the disjunction of these. I think this is supposed to be the same epsilon as this. Any questions about all of these bullet points before I move on?
It's good. We're good here.
Okay. Now let's build categories from rings. We can just take a ring, take the finitely generated free modules. So that is things of the form r to the n that I'm just going to represent by natural numbers, and our linear maps between them, which I can always represent as matrices, because I'm choosing a basis for all of my objects. So I'm not going to spend too long on this. Important things are that it has a lot of the structure in common, including coproducts, which we can describe the injections explicitly in terms of matrices. They're byproducts because products and coproducts of modules coincide. And what was, or the product of natural numbers here is a tensor product. This is what's usually called a tensor product. So it's a monoidal operation. that distributes over coproducts in the same way. Moreover, I have the analogs of the maps, the terminal map, the diagonal map, and transposes of matrices allow us to reverse the direction of arrows. So I also get these kind of transposed coproduct inclusions and diagonal maps. So I have structure that I can give the same notation, and I should be more precise about what the relationship is between these ingredients. Before that, by analogy with the idempotency observation, some of the maps from n to 1 are idempotent in the sense that I described, namely, so I glossed over this a little bit. Remember that arrows from n to m are m by n matrices. Okay, so these are just row vectors, and being idempotent in this sense amounts to all of the entries in my 1 by n matrix, i.e. my row vector, being idempotent elements in R. The relevance here is when I add this property, when I only look at maps with this property, then I can also construct complements satisfying the same equations as what we saw for complements in the Boolean lextensive category case. So you'll probably know that if I have an idempotent in a ring, then 1 minus that idempotent is also idempotent. And you'll observe that if I multiply E1 with 1 minus E1, then I get 0. So I might not have complements for every arrow to 1, but I've already isolated enough properties to guarantee that some of them exist. Okay. Some things that are also present on both sides, but that we have chosen not to include in the axiomatization of Ultrarings. One is, so I just mentioned the lack of complements for general arrows. One is that they both have finite products. So I can construct products of products in the Kleisli category just using the monoidal product and coproducts. But in mat R, in matrices, in these free finitely generated R modules, products coincide with coproducts. And it wasn't clear that the interaction between products, categorical products, and the rest of the structure could be axiomatized in a way that was common to both, that would be useful for the rest. And we haven't found ourselves using them, so we're going to omit those. And in the second case, because they're byproducts, we have pairings for any pair of maps. So this is just the usual pairing of arrows into a product. But we saw that they only exist for some pairs of arrows in the Kleisli category over a Boolean extensor category. So the observation I made earlier about recovering Boolean algebra truth values on the one hand and the ring that we started with on the other when we look at endomorphisms of the monoidal unit. Similarly with transposes, so we're only going to introduce the ingredients that we ended up using and incorporating into the logic. Okay, at this point I need to speed up a little bit. So I'm going to breeze through some technical details which are involved in the definition. But which aren't necessarily required to understand the using writing things. This is the notation that I'm going to use for a monoidal category. Isomorphism. I'm not going to talk about functors between these things very much, but it's always going to mean something that preserves the symmetry and the monoidal category up to isomorphism. The monoidal structure up to isomorphism. In describing the relationship between delta epsilon and delta star. I'll talk about Frobenius sesquimonoid, which is kind of a gross name. But the sesqui part, remember that's 1.5. So we do have a comonoid formed from delta and epsilon, as you would in a category with products. We also have that this delta star is commutative. And the interaction between them is that delta star is an inverse to delta on one side, and on the other, it satisfies the Frobenius law, which would be nicer as a string diagram. But it took me long enough to make these slides that I didn't end up having time to draw the string diagram. But if you look up the Frobenius law on the NLab, then you'll find it.
Morgan, what's the half?
The idea is, what's the
half? What's it, Frobenius? What would be the 2 that you're missing? You said that delta is a monoid?
It's because delta star doesn't have a unit for it. There's no
Okay.
neutral element in the opposite direction.
Okay, fine, a unit.
So it does have because of the direction that things are, it does have a co-unit, but it doesn't have a unit.
Okay.
I guess this is ambiguous as to what's entirely ambiguous about what's left out, but fortunately none of the other possible interpretations of what that could mean will come up. Further technical note is that we choose coproducts. So that is, not only do we have some coproduct of objects, but we have a chosen one. And what I mean by it being chosen is that the coproduct injections form natural transformations to the coproduct to input functor. So I have a functor that takes C cross C to C, it takes coproducts, and we have these natural transformations. I'll explain in a minute why that turns out to be weirdly relevant. And I mentioned distributivity a few times. So here's the formal definition of that, namely that this arrow that you can always form in one of these categories where I have both a monoidal product and coproducts, that this is an isomorphism. Okay. So, wow, there's even one more slide of technical details. Apologies. So this is the notation I'm using for zeromorphisms. I've already mentioned zero objects, so that should have been earlier on. I can define co-injections. So this gives me an alternative way to characterize iota star that I pointed out that we could construct in both of the cases earlier. And this is the relationship that we get when we compose iota with iota star in the 4 possible ways that we can do that. And finally, I've also talked about pairings earlier on. So formally, that's saying an arrow such that when I compose with iota stars, I get the arrows back out again. So I need these iota stars just for the definition of pairing to make sense. Okay. So finally, I can tell you what an ultra ring is. So none of this should surprise you at this point. I have a distributive monoidal category. So that is a symmetric monoidal category with coproducts and a zero object where the monoidal product distributes over the coproducts. And such that each object is equipped with the Frobenius sesquimonoid structure that I described earlier. We've seen concrete instances of all of these. And the reason that I needed to choose coproducts is that these equations feature coproduct injections. As a consequence, if I could express an object as a coproduct in several ways, then that would impose extra equations which we don't want to hold. Like we only want this to be true with respect to the naturality squares that we have for the iotas, and not for arbitrary decompositions of an object as a coproduct. Okay, what's the extra stuff? This one is a little bit important. It says so. So this is a way of constructing a graph from f, from an arrow f. I can use delta star to perform the operation that I would if I was just drawing the graph as a span of arrows in a category. And this is saying that if the graphs of two arrows are equal, then they're equal. And the second one is the idempotent condition that we've already seen. So it's saying that this pairing exists when I have an idempotent P into the monoidal unit. Okay. Because none of this is surprising, I'm not going to spend more time showing it to you. I'm just going to move on. Okay, we can define functors between these things. They're as strong as is reasonable. So we make things equivalence invariant, but we still insist that things are isomorphisms. The notation is not going to be used anywhere else, so I don't need you to absorb this. Just the notion of functor is what you'd expect, and we can build a two category out of them. So implicitly later on, we're going to be working in that two category. Recap what we've done. Provide two examples of categories with similar enough properties that we were able to find a mutual axiomatization of the structures that we found inside them. So now what we'd like to do, and it's going to take more time than I have to do it properly, so I'm just going to sketch the steps, and I'm going to have everything on the slides so that someone that's watching back later can pause and read the detail if they like, or read the paper if that would be a bit clearer. We want presentations that directly produce this kind of category. Now, because this kind of category, quote unquote, has a lot of structure, it takes a lot of work to build up the structure out of the basic ingredients that we want to generate them from. So I'm going to focus on those basic ingredients, and then step by step, I'm going to build up to a syntactic category. So the analog of what we did with first order logic to get to Boolean lextensive categories. We're going to have a presentation that we're going to build an ultra-ring from. And that will give us what we need to lift what the type of theory or the specific theory I mentioned at the beginning, the theory of strings, to a context where it can also be used to talk about examples coming from commutative algebra and not just computational problems, or not just the oldest kind of computational problem that was considered. Now, I'm not expecting that outcome to be that surprising. If anything, what we were trying to do was come up with a categorical framework that allows us to talk about different families of computational problems at the same time, or at least in a uniform parameterized way. So here's the data that we're going to generate things from. We again have a collection of sorts, and we're sooner or later going to allow ourselves to tensor these together. And then we also have a collection of generators, and we're thinking of these as arrows of this particular type. So we know that eventually we're going to be interpreting these in a category which has monoidal products and coproducts. We're actually missing, when we want to build an ultra ring, is a way to talk about maps that go into coproducts, and that's what these generators will give us. So in order to talk about the contents of these sorts, we produce variables. So a variable will have a type A, and using these variables, we can construct progressively the analog of formulas. So these are the basic formulas that we're going to allow. In first order logic, we would have called these atomic formulas. But on the ring side, these would be the equivalent of monomials. And that's the name that we're going to borrow. So even though these have equal signs in, we're thinking of these as the analog of monomials. Okay, so this index ranges over sorts. This G upper J, this J is an index. So it's saying the Jth component of this generating arrow G, which is to say what we'll get by composing eventually with the co-injections, the iota stars that I mentioned previously. So we need everything to map up in the way you'd expect. This integral sign is a binder. So x becomes a bound variable within the expression a. And if you're familiar with how we manipulate variables in first order logic, we can replace this x and all instances of it in a with a y everywhere, and it's considered the same formula. We have some abbreviations for when we want to integrate over several variables at once. We have conventions for what happens when we want to integrate over no variables, and so on. So there's a lot of rules for, as always happens when you're introducing new syntax, for how the different constructors relate to one another. But all of it's reasonably intuitive from the way we've presented it. So to give a bit more intuition before I complicate things, these should correspond to these and these. And we've already seen where, for example, this 1 minus p comes from. Was there a question?
I have a question. So where's the addition in the ring setting corresponding to?
Good question. So from these monomials, we're going to take formal finite sums.
Nice.
And that would be the sum in the ring. And
Yeah.
also allows us to introduce 0. And finally, we introduce contexts, which is just an association between variables and types. And for any logicians that are watching, this kind of slide is not unexpected. We have rules which say how we can produce a context, a valid context for a given monomial in this instance, and then by adding just that sums behave as formal sums to these pre-polynomials. So now we have not just the formal expressions, but the types, and we'll need those types when we want to think of these formal expressions as arrows. Okay, we've got these pre-polynomials. The problem is that several of them could or should identify the same arrow in our Boolean categories. So some of them for formal reasons, and others for quotienting reasons. We want to be able to express equations between these things, and for those equations to hold in the category that we're going to build. So I'm going to accelerate now. I don't want you to think that you should absorb the contents. It's just the formal underpinnings that allow me to do the thing I just said, namely be able to identify expressions corresponding to identical arrows, or things we want to be identical. So unsurprisingly, we have some congruence. It says some syntactic things are equal, but also, so that includes this one, but also when we multiply by things, we're invariant on the right. We can expand contexts, and we can also reduce contexts by eliminating anything that's not used on either side. The binding, the binder that I mentioned allows us to eliminate something from the context. And finally, we have cancellativity, but I don't think I'm going to use in the talk. And it's been long enough that I can't remember what we do use it for. But it's there for whenever that might come up. Incidentally, this makes handling infinitary Ultrarings a bit more complicated. So it's something I've tried to get rid of, but I haven't worked on this for a while, so I can't remember how successful I was. Okay, the final thing we need is compatibility that's derived from congruences that says when formal sums of monomials should be well typed, so are compatible with each other when I can construct an arrow into a coproduct out of arrows into the components. So this relation is a compatibility relation. There are some rules. Next slide. Don't try and absorb the contents. The punchline is that I end up with this notion of annular theory, where I have sorts and generators of the kind I mentioned earlier. I have equations. So there are the basic ones which are supposed to be included. I'll go back a couple of slides for that. So there are the ones that are purely syntactic, that say how the different constructors interact with each other. And then I can add my own equations to express which things I want to be identified. And then P and Q are pre-polynomials matching gamma such that, right, sorry, important important other thing on this slide is the condition for a pre-polynomial to be a polynomial, or rather the reason I called them pre-polynomials, is that I require that the monomials featuring in a formal sum be compatible with each other. Just to clarify what this compatibility condition is supposed to be, I mentioned that in the two motivating instances, some pairings of arrows exist. And so this compatibility relation is the relation that says the pairing of Q and R should exist in the category that we're going to construct. So we have some sufficient conditions, and if the pre-polynomials, or rather the monomials in them, verify adequate conditions, then we can also deduce that they should be compatible. Fast talk over. From these, when I actually want to build a syntactic category that's going to be an ultra-ring, first I need to tell you what the objects are going to be, constructed from the sorts. So I can take formal tensors of the sorts, or rather I can take formal sums of formal tensors of the sorts. And when I take a tensor of sorts, I want to think of a variable in that tensor as just being a list of variables of the sorts that appear. In summary, the arrows in the syntactic category that I'm going to build, the ultra ring that I'm building from this syntax, I've already forgotten the start of my sentence. The ultra ring I'm going to build from this syntax consists of objects which are formal sums of formal tensors of the generating sorts. And the arrows are going to be matrices of these polynomials up to equivalence determined by the equations, which I've spent all these slides constructing formally. Now, the passage from the data to the sorts was kind of gross. There was a lot of technical details, and what I want you to take away about what we've achieved as a result is that all of those technical details get packaged into this construction. That is to say, I now only need this signature, this annular theory, sorts, generators, and equations, in order to present an ultra ring.
Why'd you call it annular?
Annular from the same root as ring. So in French, ring is anneau.
Of course.
Yeah. There's at least one person that's found that not a very nice name, but well, the paper's published now. So obviously, implicit in the claim I was just making is that what we end up with really is an ultra ring. So I have to say how composition works, and it amounts to multiplication of matrices, which is nice because it intuitively connects to one of the motivating examples. But there's obviously work you have to do to show that this is a valid product of matrices, that this is a valid polynomial in the sense described previously. So again, there's a lot of work that goes into this construction, but having done it at this level of generality, we're free to just talk about these annular theories, and we have some guarantee that what we're going to be able to do is what we expect to be able to. Okay, so I'm now going to go over time to actually get to the complexity part, because I'm sure that there are some people who have been waiting for it. So I mentioned strings earlier. We talked about this presentation. Now, if I want to present this as an annular theory, I don't have an intrinsic notion of proposition, but what that should be is arrows into the monoidal unit, which satisfy the idempotency condition. Now, I could just ask for things to the monoidal unit. This is strictly stronger. This is the notion that we use. And then we also need to adapt the axioms for the ordering, which is represented by L here. But we can do everything without having to take any unexpected detours. The theory does really just translate from first order logic to this annular logic. So with either definition, we can think of a problem, like a computational problem, as a set of strings, a subset of all of the finite strings. And that's the context that we're going to talk about complexity, namely the problem referring to determining whether a particular string belongs to that collection or not.
So you have a translation of every first order theory into an annular theory? Is there a formal statement there?
There isn't one that's written down, but the syntactic analogy that I gave earlier for monomials essentially tells you what you need to do. So conjunctions become products. Existentials, with the caveat that they have to be provably unique in a way I haven't explained, will become these integral binders. So the translation is straightforward, but we will surely, in the not too distant future, write down the formal statement, because it would be useful to be able to just translate directly, right?
Thank you.
Okay. So I've introduced this notation F1. Now, it refers to finite sets. I introduced it on the previous slide. There is a meaningful sense in which we can identify this with the field with one element, the hypothetical field with one element, but I just don't have time to explain that in any detail. So just think of it as alternative notation for the remainder of the talk. So now we have different kinds of extension of the theory of strings, and we're thinking of these extensions on the categorical side. So as functors out of this syntactic ultra ring to some other ultra ring. So there are three different types of such extensions that we want to consider. One is what we get by adding finitely many sorts, generators, and equations. So literally expanding the theory of strings. One is the same. Actually, it doesn't really matter whether we include the finiteness condition or not, because I'm going to be talking about plain finitely presented things anyway. But the kind of theory that we get by adding no extra sorts. And then there's one more property that if you look at the paper, you'll see why I didn't include in the slides. But the point that there is a concrete description of different kinds of extension. And we can use those.
Is F1 by itself just on the empty theory?
That's right. Hey, maybe I can skip past the end. I have to skip back to exactly the right amount. Okay, this is getting skipped. This is a definition of an algebraic definition of machine that we use in the paper in order to more explicitly make the connection with complexity. But what we actually do with it is just take this presentation of a machine and we transform it into a theory, right? That's what we want in the end. We want some theory where the models of that theory are exactly a string and a machine, such that the machine accepts the string. So implicitly and explicitly in the paper, we construct a theory whose models are these things, and which we view as an extension of the theory of strings by just including the string that is part of the data. And the final output of all of this work is that we can identify a problem as being in one of these complexity classes, if and only if it is presentable as an extension of the theory of strings with one of these properties. So in one direction, we build this theory X, and we show that it has these properties. But equally interesting is the other direction, which says that these properties are enough on their own. Like, I don't need to build these as presented super complicated instances. These properties actually characterize those complexity classes. Now, I'm sure there's questions that you would ask me about that if I told you enough to ground such questions. But I can at least give you a little bit more information. Firstly, an excuse for why that extra isn't present. Second, that the reason that it's obviously still difficult to determine whether P is equal to NP is because the property that's involved here in saying what it means to be in P is extremely intricate. Like, it involves a bunch of recursive definitions. So you couldn't just take something a finite presentation. It's fairly easy to show that whether or not there exists a theory of finite presentation for your problem, and show that it can actually be expressed to a theory with this property. That's the hard part that is still just as mysterious as it ever was. And the result that was one of the main results of the paper is that where I've written F1, I could actually have been working with the ultra ring derived from a ring, with the caveat that it has to have no non-trivial idempotence. I can replace F1 with that everywhere. So I can also recover and characterize algebraic complexity classes. So one's defined on algebraic machines, meaning instead of zeros and ones in all of my entries, I have, say, real numbers or elements of some ring. And my basic operations are going to be the ring operations on those. I can reproduce this characterization for those complexity classes just by making the definitions parametric. So that was the result that we were aiming for in the first instance. And as a hint of where we want this to go, I mentioned algebraic geometry right at the beginning. The point is that we know that when we turn the arrows around in the category of commutative rings, we have objects that we can both describe geometrically, but also we can embed into a larger setting of geometric objects, category of schemes. And having those extra objects at our disposal, not our disposable, allows us to learn more things about the basic objects. So we're hoping to exploit a similar approach in trying to understand complexity theory as expressed through Ultrarings. That's it. This is the paper. I also mentioned a paper of Lorvier early on. None of the other references ended up coming up. Thank you very much.
Thank you. Any questions? I have a bunch of questions.
Why ultra?
Why ultra? Well, clearly it was a mistake in the sense that I confused myself in writing the title of my own talk. They don't have very much to do with ultra categories besides the connection through classical first order logic. So you might know that ultra categories come up are an axiomatization of categories of models of classical first order theories. So there's some vague justification of the use there, but in that case, the ultra is a connection with ultra products, so categories where we can form ultra products, and there's no relation between those and this. Otherwise, it's hard to find prefixes that express your enthusiasm for the generalization that you built. So just for lack of a better name, maybe if the theory gets far enough away from this initial presentation, then the name will be changed, but we'll see.
You can go. No, you go. Are you sure?
Yeah.
Okay.
Speak up.
So can I think of a string as a as a scheme, and in particular, like in other words, a problem? You say a problem is a string. So can I think of a problem?
I described a problem as a set of strings.
Okay. Well, a set of strings. Can I think of a set of strings or a problem as a scheme? In other words, if you have a problem that you want to solve, like, I don't know, some satisfiability problem, then you can regard that as finding an F2 point on a variety, right?
That's right. So that's what this picture is supposed to be conveying.
Okay, so you are
this is a point, and this is saying
thinking,
that the point factors through the sub variety.
right? Yeah. Okay. I just want to check that the way that I'm thinking about this is the same way that you're thinking about this. Okay. And then in other words, any problem, you're saying basically I can regard a problem as a variety or a scheme. Let's be a little bit less specific. And then you're taking that scheme and you're able to kind of classify it into either P versus NP in some sense. Like that's
sure. So the properties I gave were properties of the map in the opposite direction, but that you can equivalently express them as properties of this arrow. So the result, as I stated it, is saying if this arrow is of finite presentation, so maybe quasi-coherent would be a good analogy, although I'm not sure how precise that is. It's like saying if I have something that's quasi-coherent over this would be an A1, I guess, or an AN, or the disjoint union of all of the A to the N's. The
you mean
so depending on this property, I can say that the problem of the lifting problem, if you like, I've turned a problem expressed in terms of models of theories into one of finding a lift, and the difficulty of that problem is determined by the properties of this arrow.
Okay. And then, but then like in principle, right? Like if so like, but how practically can you do this? Like suppose I hand you some variety or some system of equations that represents a problem, right?
Yeah.
Can you use this? Can you use what you're saying here to realize that problem as being in P versus NP in a practical way, or no?
So returning to the statement again,
Okay.
showing that something is in NP is actually really easy with this result, because if I'm able to, if you give me a theory and I'm able to find a presentation of that theory, it's probably going to be a finite presentation. I mean, if I'm able to find it in the first place, or if you give it to me in that form, I'm going to easily be able to tell whether it's a finite presentation or not just by looking at it. This inductiveness property, I don't think that you could check it at all. This would be, you give me a theory presented already in a form that lets me see that it's in P, and not something that I can easily tell from an arbitrary theory whether or not it's the case. So just to give a vague idea of what inductive means, the equations in the theory have to be organized organized recursively in a particular way. So each equation depends only on the ones before it in this ordering, and the ordering is nice enough. So checking that that's the case for a generic theory that you might hand me is not going to be straightforward.
Like a little bit more specifically, I don't know how specific I'm allowed to be in some sense. Like if I want to solve a system of linear equations, then I'd be able to see that that's P. You know,
Okay, so more concrete
the theory
example.
of a system of linear equations, then it's definitely in P.
Mhm.
Right? Because in that
Yeah.
case, I guess it's quote inductive because you could do like Gaussian elimination or something and then do, and that's going to be your inductive thing, right? That does that make any sense?
I think if things were linear, you wouldn't even need to go put in that much work to prove that something was inductive. Yeah.
Okay. So like, I just want to get a feel for what you proved in some sense. I see. Okay, but then otherwise, it's sort of generic system of equations, then yeah, I mean, who knows? It's hard to tell if it can be if you can do essentially like Grobner basis sort of reduction technique to see that it's inductive in some sense is hard. And like, is it as hard as doing like elimination theory? Is that the same thing or no? Like, is that the difficulty in some sense? I give you a theory. A theory for me is a scheme. It's always a scheme. And then I ask you if it has an point or something. Is basically all of the difficulty doing like a Grobner basis calculation or no? Do you know what I mean by this?
I haven't done enough of the calculations to either of Grobner bases or of trying to rewrite a starting presentation of some theory into one with the desired properties to be able to answer definitively yes. Superficially, it feels like they're similar problems, but always it's going to be like there might be some order. If you give me an infinite list of axioms, there might be some ordering of those axioms that makes it inductive, and it could just be very difficult to find, right?
I'm gonna guess. I'm gonna guess that your if and only if is essentially something about like elimination theory. Like a theory is a scheme, and then doing some elimination theory on the ideal that defines that scheme, and determining whether it's in P or NP is basically going to be how hard it is to do that elimination. In some sense, I don't know how
I kind of hope that you're right.
I'd be curious.
I will say that the intuition that we use to get to this result is more along the lines of exploiting what we hoped to exploit was the existence of p-complete and np-complete problems. So the point being that if I'm here, I want to be able to say I have some other problem, maybe even over a different theory. I want to think of an NP problem over a given theory as one which is a pullback of an NP-complete problem. And by trying to characterize what those problems look like, that's how we came to this property in the first place.
I see. So you always relate it to the problem, basically. Yeah.
Sorry,
Amelia, do you have a question?
Yeah. You said the proof was non-trivial, this theorem. Is that because it runs through like the descriptive complexity results, like Fagin's theorem?
Good question. Do I still have it open? See, I do have it open. Let's see which theorems we explicitly cite. So, I can actually justify the non-inclusion of inductive, which is all of this. I'm presuming you can still see my screen.
Yeah, I can see it.
So let's see if Fagin's theorem is mentioned. Okay. Logical part describes the BSS machine the transfer of Fagin's and Emmermann's logical characterizations. So it's right. This is described using descriptive complexity, theorems from descriptive complexity, in order to as a very big shortcut in proving that this works.
Okay. That makes sense. And then are morphisms?
No, that's it.
Can you hear us?
Morphisms? Say that again?
Are morphisms between these theories like reductions between problems? That's what you were kind of alluding to, right?
Yes. So there are the see, I talk about algebras at some point. Right. So I can think of this as an extension of the theory, or a model of the theory, or what was it you said in your question? What was your
So
description?
I'm thinking of an algebra as a set of problems or a set of strings, right? So a complexity class. And then I want a morphism between complexity classes to be like a reduction. Although I guess that doesn't really make sense. Yeah, anyway, I was just thinking about like if there was a relationship between morphisms and reductions.
So yes, if a reduction can be presented syntactically, that is, I can give a crisp enough description of the problems that I can formalize it into syntax and express the reduction as interpretation of one syntax and the other, then explicitly you can do that. But based on how complexity theorists work, that's typically not viewed as worth the effort. Like having a reduction is already enough to give the relationship.
Right.
But that perspective will be more useful when we're avoiding the explicit presentations of the problem in the first place. Knowing that we can think of these errors as reductions will be useful.
Okay, one more thing. So you have these annular theories and ring presentations and first order theories embed into these annular theories, right? Right.
Mm-hmm.
And then so what is
yes, I claim that.
So what should I think of the ultra ring generated by like a presentation of a ring? Like, will it just give me a ring, or it'll be some very complicated category?
Will literally be mat R. So here I also mention, I say this will be meaningful for general ultra-ring R. Specifically, when I take a commutative ring and I consider the finitely generated free modules. I think I talked about projective modules, and I think those also form an ultra category. But it turned out that the one that when I wrote the abstract, I thought that we were shifting towards projective modules because it wasn't clear if we were going to want to split all idempotents or just these kind of monoidal idempotents. Anyway, aside over, if I take that mat R from earlier, then that already is an ultra ring, and I can extend it by adding sorts or generators. So extend it as an annular theory, and the same construction works. So I end up with strings being, rather than just finite sets with a total order and where did I put the strings? They're here, right? Rather than just having a proposition that tells me where the zeros and ones are, now I literally have a valuation that tells me not only which things are not zero, but gives them a value in the ring.
Thank you.
Anybody? Any other questions? Anyways, if not, let's thank the speaker again. Thank you very much.
Thanks for having me. Sorry about the
Morgan,
connection issues.
it's okay. It's okay. We saw Margaret. If you want, you could send me a new updated abstract. So I'll post the thing with the new abstract because it's different than what you know. If you want, otherwise I'll just change ultra rings to ultra.
Yeah, I'll do that. I'll just there was also some weird typographical things in the abstract as well, so I'll do that right away.
Anyways, thank you very much. Next week we do not meet, so the next meeting is in 2 weeks. Anyways, ladies and gentlemen, it's a pleasure. Have a wonderful week off break. Anyways, I am here. Okay, take care, Morgan. Nice meeting you. Thanks.
So I think you were doing this remotely.